Hello everyone, my name is Shah Ghazanfar Ali and I am a third year PhD student. I am currently doing my PhD in INSAM and the University of Genoa. Actually, my PhD is under co-title agreement between University of Genoa and INSAM. So according to the agreement, I am supposed to spend part of my time of PhD in France and part of it in Italy. Today I will be presenting one of our published paper about simulated annealing based fitting of CAD models to point cloud of mechanical parts assembly. The co-authors with me are Mr. Ravana Palet, Mr. Jean-Philippe Bernal, Madam Franca Giannini, and Madam Marina Monte. So I will start my presentation with the research question, background, and followed by objective, methodology, and proposed approach. And at the end, we will discuss result analysis, conclusion, and some future works. The topic is related to reverse engineering, in which we obtain a point cloud that is coming from a laser scanner. It could be in the form of points or could be as a mesh. So here you can see in the picture in the green, there is a point cloud composed of many points. On the other side, you can see a mesh that is also coming from a laser scanner. So the question is how to reconstruct CAD part or assembly by segmenting a point cloud of a mechanical assembly, so as to allow as-built verification of tolerances without disassembling, or to reconstruct a parametric CAD part or assembly without patch-by-patch fitting. In the existing methodology, actually it is not that easy to reconstruct a part from a point cloud of an assembly. If we have to reconstruct a part from a point cloud of an assembly, first we have to disassemble the part from the assembly, and then we have to scan the individual part so as to obtain a point cloud of the single part, and that point cloud can be transformed to a CAD model. But it's not that easy to reconstruct a part from a big point cloud assembly. So the goal is to reconstruct or do as-built verification of tolerances, or to reconstruct a part from a given point cloud of an assembly. For the background, I will start with the brief introduction of reverse engineering. So in the traditional reverse engineering, the process starts with the existing object. Then there is data acquisition with the help of contact and non-contact devices. The output of these data acquisition devices is point cloud that incorporates noise, and there is some pre-processing that is required to remove such noise and also to merge different segments of points. And after pre-processing, the output is a point cloud that could be in the form of STL. Once we have this STL, we perform some extra tasks like feature extraction, segmentation, and surface fitting so as to obtain a CAD model by the end of this process. On the left-hand side, you can see a car model is being scanned with the help of a laser scanner. The output is a point cloud that is composed of almost 40 million points. And then we require some data treatment so as to transform this point cloud into a CAD model that is composed of different surfaces which are joined by different operations. Actually, these two steps, feature extraction and segmentation and surface fitting, is not that easy. It requires skill, it's time consuming, it's tedious. There are some issues of accuracy, there are some issues of patch by patch fitting when we are talking about joining different patches. Of course, then there are some issues of tangency. Many times the user are left with gaps which are not easy to fill. And most of the work is for the simpler part, not for the complex one. The objective over here is to bypass the existing traditional reverse engineering that starts from a given scan of an object or assembly and later it goes through different operations like preprocessing, feature extraction, segmentation, surface fitting to obtain a CAD model. The CAD model obtained through traditional reverse engineering are mostly dead models, which means they cannot be modified for their features on the later stages of product development processes. So the goal is to have a new methodology to generate editable CAD parts that starts with the point cloud that is coming either from a laser scanner in real case scenarios, or it can also come from a virtual scanning. Actually, virtual scanning is a new way of generation of point cloud in which CAD models are transformed to point cloud, and later these point clouds are incorporated with different artifacts like noise, outlier, misalignment. The end product of this virtual scanning or the point cloud as if they are coming from a laser scanner. So we can tune this virtual scanning with the given laser scanner by playing with the parameters of this process of virtual scanning. Actually, we have already published a paper on virtual scanning in which we can generate a point cloud as if they are coming from real laser scanner. This is useful in the current research because in this way we can generate many point clouds without actually performing the real scanning. This is fast and easy way of generation of point cloud. Of course, these point clouds are not just simple point clouds, but they do incorporate different artifacts, as I told. The artifacts are close to the real laser scanners. So as soon as we have a point cloud, the user requires a CAD template, a parametric CAD template that is coming from a database. So having a CAD template and a point cloud, we need an optimization process that will allow to fit this CAD template to a given point cloud by playing with the parameters of this CAD template. The optimization process minimizes the energy between the CAD template and the point cloud iterative-wise. Try to minimize the sum or square of distances between the CAD template and the point cloud throughout the optimization process. By the end of this process, we obtain a fitted CAD model, or we can say a reconstructed CAD model. And this CAD model is an editable CAD model that can be utilized in product development processes. We have a real features tree in a CAD modeler for such kind of reconstructed CAD templates. The proposed methodology starts with the existing object that is transformed to a point cloud with the help of a laser scanner, or it can also come from a database of parameterized CAD model, as I earlier discussed, that we can generate point cloud with ASCAN point cloud generation strategy, in which a CAD assembly can be transformed to a point cloud. Once we have this point cloud, the next step is to choose a CAD template that needs to be fitted with a given point cloud. After choosing the CAD template, the user is also required to pre-arrange this CAD template with a given point cloud, and after pre-arranging, he is also responsible to put some initial values to this CAD template before starting the optimization. This initial value means that before starting, he needs to put some rough dimensions for certain parameters close to the final position, not exact one, of course. We do not know the exact final values of this parameter, but we have to put some initial values before starting the optimization loop. Once the CAD model is prearranged and rough dimensions have been chosen for CAD template, we can start our optimization loop. The objective of this loop is to find out the optimal values of parameters of CAD template so that the CAD models best fit with the given point cloud. For this purpose, we have chosen simulated annealing algorithm, which is a meta-heuristic algorithm that is able to solve optimization problem in a large solution space. Simulated annealing algorithm has demonstrated good proficiency to find efficiently the solution from a prearranged configuration. It performs a global stochastic search that evolves towards local searches as the time goes on. So for every iteration, simulated annealing suggests new values of the parameters of the CAD template. After this suggestion, the CAD template is updated and tessellated. We can also use ICP for this updated and tessellated CAD part for translation and rotation metrics that will align the CAD part with the given point cloud where it needs to be fitted. After ICP, again, the CAD template is updated and tessellated to perform the task of distance computation, which is the core of this optimization algorithm. Actually, the distances are computed between the CAD model and the point cloud as a sum or square of distances that also work as energy that is minimized throughout this optimization loop. This optimization loop works in an iterative way until the optimization could not further minimize the distance between the CAD model and the point cloud. We also have a parametric loop for the cases where the part is complex or there are many parameters. After some research and study, we have divided the parameters into three groups of parameters. The first group is for the structural features, for example, pads, pockets, revolutions. The second group belongs to the detailed features, for example, hole, ribs, and the last one is for the scanning features that involve fillets, chamfer, and etc. For simpler parts, actually, we do not need these parameters where there are very few. Actually, we do not need this parameter loop in case where the part is very simple and where there are very less parameters. So all the parameters can be taken care in just one group. We also have a segmentation loop. Actually, for this, the first figure, when I prearranged the CAD template with the point cloud, you see the red points highlighted. These red points are highlighted. It means that these are the points which will take part in the optimization when the CAD template will be optimized. The selection of these points are actually based on threshold distance, which is measured from the pre-arranged CAD template, which is set up to 10% of the diagonal of the pre-arranged part-oriented bounding box. This percentage corresponds somehow to the level of confidence in pre-arrangement. Thus, the default value can be adjusted. So the segmentation loop may run several times, maybe for each parameter group or for each optimization loop. Okay. In case of global fitting, where we don't have local fitting, we do not need segmentation because we don't need to segment the point cloud. So after running the segmentation loop, we have our fitted CAD model. It could be a single part or it could be an assembly. For multiple parts, we can perform the same optimization loop. Also, we can now compute the deviations. As I said earlier, that the point cloud in the beginning has been generated with the help of as-can point cloud generation strategy, which means that when we generated this point cloud, we already knew the dimensions of the assembly which was used to generate this point cloud. So now we can compute the deviation between what we obtained at the end of this optimization and what it was before running this optimization or before generating this point cloud. So in this way, running these examples on as-can point cloud generation strategy, this kind of also help us to improve the efficiency and know how better fitting is done using our methodology. So you can see in this figure that two flanges are fitted simultaneously using this proposed methodology. Of course, there are also some assembly constraints like distance constraint, parallelism, concentricity between two flanges, and these assembly constraints are also optimized using optimization loop. So first we have fitted these two, for assembly fitting, we have fitted these two flanges. Later we have fitted these two bolts. Of course, these bolts also involve some assembly constraints like concentricity between the slender of the bolt and the hole. Also, there is this face coincident constraint between the head of the bolt and the face of the flange, and these two bolts are fitted simultaneously again. Next, we fitted two screws, again involving some assembly constraints, and then the central part and the top plate and bottom plate. The consistency of this constraint or these assembly constraints is throughout maintained by CAD modeler. For every optimization loop or every iteration, CAD modeler actually takes care of this assembly constraint. And using this methodology, I think it's a good way to reconstruct assembly. It's a new way. It's not like traditional one. And we have a very good promising result with this. And now moving to the result section. The first example is for the fitting of sonot hard with the real scan. The point cloud is obtained with the help of a laser scanner that is Romer Absolute Arm 7520. The number of points in this obtained point clouds are about 257K. The CAD template for this example is controlled by about 10 parameters. So we have divided the parameters as I discussed earlier according to level of details they belong to. So there are structural parameters, detailing parameters, and scanning parameters. In the table on the right side, you can see these parameters have been divided into three groups, G1, G2, G3. For fitting this CAD template, the CAD template has been prearranged with the given point cloud in figure B, and then putting some initial values for different parameters before starting the optimization. The final fitted values are also shown in the table. Here we do not have the deviations because we don't know the real values of this real object. But visually you can see the fitting is very good for this global fitting, and the part is well fitted here by the end of optimization loop. The next example is for the fitting of robotic arms for different position. This example is actually very interesting in terms of Industry 4.0, where the user needs to maintain the coherence between the physical system and its digital twin. Actually, there are three positions, and the robotic arm is controlled by three angles to track those three different positions. This example is a bit different from the last one, where here we are not updating actually the CAD model or recovering CAD model, but we are updating just the assembly using assembly constraints to track different positions. The robotic arm is supposed to stop during the update of its digital twin. So the idea is to track different positions using our optimization process. So for the first set, the G1 or the move 1, the CAD template is prearranged, and then it is updated using three angle alpha, beta, alpha 1, alpha 2, and alpha 3. You can see the final obtained values, and deviations are quite low because these point clouds are also generated with the help of ASCAN point cloud generation strategy, and the relative errors are also very, very low by the end of this process. So different positions have been tracked using our proposed methodology. The last example is for the fitting of flange. Actually, this was the one you also saw in the overall proposed methodology. First two flanges are fitted using assembly constraints and the parameters of the CAD template, and later two bolts are fitted, again assembly constraints, then the nuts, central part and top plate and bottom plate. You can also see here a segmented point cloud that are obtained by the end of these optimization loops using segmentation loops. These are the points that remain by the end of the process, and in this way we are also performing the segmentation. For conclusion and future work, for conclusion, I would say the fitting is for simultaneous fitting of several parts, and also for the single parts. The resulting CAD models are editable. We are bypassing different data manipulation. Process approach can be used for global and local fitting. The proposed approach is modular, and each model can still be further optimized or improved. For future works, we are working on energy minimization by putting weights for functions on small features, because small features, they contribute very less in the overall energy because they are very small, and that's why sometimes in some cases they are not well fitted. So this step is very important. We are also thinking to work on initialization of initial temperature for simulated annealing in an automatic way, maybe using artificial intelligence. Also to perform sensitivity analysis on different parameters to see which parameter are contributing more or less on the overall energy. And also the work is also going on the fitting of 2D also instead of 3D, where the curves can also be fitted with the given reference curves. So it's a new kind of reverse engineering in which not only 3D parameters but also 2D parameters are also fitted, or also not only parameters but features are also can be fitted. If you have any question, please do ask.